This video is for topic 7.7, calculating equilibrium concentrations. The objective for this topic is to identify the concentrations or partial pressures of chemical species at equilibrium based on the initial conditions and the equilibrium constant. So we're going to use our equilibrium expression, but instead of solving for our constant, we're going to use our constant and some known information to solve for the either concentrations or partial pressures at equilibrium. So we're going to use the same equations, we're just solving for something different.
This question is looking at the reaction between nitrogen and oxygen that contributes to air pollution when fuel is burned in a gasoline engine. And so the question tells us that at 1500 Kelvin, the equilibrium constant is 1 times 10 to the negative fifth. So we're going to look at a sample of air that has a concentration of 0.08 molar nitrogen and 0.02 molar oxygen at the beginning before any reaction occurs. And then we want to know the equilibrium concentrations of the reactants and products after the mixture has been heated to 1500 Kelvin. So we're going to still use an ice table. We're still going to use our equilibrium constant expression, but instead of solving for our equilibrium constant, we're going to be solving for concentration instead. So we're going to start with our ice table. So initial, change, and equilibrium. And we're given our initial concentrations of nitrogen, 0.080 molar, and oxygen, 0.020 molar. And NO is going to have a 0 concentration to start with. Now, the change is going to be minus X for nitrogen, minus X for oxygen, both have coefficients of 1, and plus 2X for our product because there's a coefficient of 2. So that means at equilibrium, our nitrogen concentration is going to be 0.08 minus X. Our oxygen is going to be 0.02 minus X. And our NO concentration is going to be 2X. Now we don't know the value of X. That's ultimately what we're going to be solving for so that we can find our equilibrium concentrations. So we're going to use our equilibrium constant expression to be able to solve for that. So we're going to start by writing our expression. So Kc equals, we're going to do our concentration of our product, so NO squared, because it has a coefficient of 2, divided by the concentration of our product, or our reactants, N2, times O2, because they both have coefficients of 1. And then we're given our equilibrium constant, which is 1 times 10 to the negative fifth. And then we can plug in our equilibrium, what we know right now. It's not the values, but it's the values in terms of X. So our NO is going to be 2X, and that'll be squared, divided by 0.08 minus X times 0.02 minus X. Okay. And now we are going to end up with, we're solving for X is what our task is. And what we're going to end up doing is dealing with the quadratic formula. So on the bottom, you might notice that when we factor those two, our concentrations for nitrogen and oxygen, we're going to deal with a quadratic equation. So we're going to have to dig back into our math skills for a little bit here. So our top is easy. 2x squared is 4x squared. Our denominator becomes 0.0016 minus 0.1x plus x squared. Okay, so now we are going to multiply our denominator by itself so that it cancels out, and we're basically going to move it to the left side of the equation. So we're going to end up with 1.6 times 10 to the negative eighth. So we're multiplying our quadratic equation on the bottom by our coefficient, or our equilibrium constant. So here we can simplify this. Let's erase this part. And we'll shift this guy over. There we go. So now that's the equation that we're solving. So we're going to take this bottom piece here and multiply both sides by that equation so that it gets it out from underneath the fraction. So we have 1.6 times 10 to the negative 8th minus 1 times 10 to the negative 6th x plus 1 times 10 to the negative 5th x squared equals 4x squared. And then we know when we're solving a quadratic, we need to set it equal to 0. So I'm actually going to shift everything over to the right side, just so that I end up with some positive numbers instead of negatives. So I'm going to end up with 0 equals, and so I'm going to subtract 1 times 10 to the negative 5th x squared from 4x squared, which when I account for significant figures still gives me 4x squared. And then I end up with plus 1 times 10 to the negative 6th x, and then minus 1.6 times 10 to the negative 8th. Okay, so now I'm going to use my quadratic formula. So however you know to memorize the quadratic formula, or whether you have it programmed in on your calculator, whatever way works. So we're solving for x. Okay, and so we end up with two values because we're going to end up with x when we do the addition, and we're going to end up with x when we do the subtraction. So we end up with 6.3 times 10 to the negative 5th, or negative 6.3 times 10 to the negative 5th. Now, x, remember, is our change in concentration, or it could be the concentration itself. So it's not going to be a negative value. So we automatically know that we can get rid of that one. It's going to be the positive value. So now we know our value for x. X is 6.3 times 10 to the negative 5th. So we can go back up here to our equilibrium line, and we're going to plug in x for each of those amounts. And so that gives us our concentration of NO is going to be 1.3 times 10 to the negative 4th. And our concentration of O2 and N2, when you take into account significant figures, you're still going to end up with 0.020 and 0.080. Because when we take into account that we have two significant figures, a change of 6.3 times 10 to the negative 5th isn't going to be a big enough change to change our numbers. So when it says calculate the equilibrium concentrations, our concentration of N2 is 0.08, our concentration of O2 is 0.02, and our concentration of NO is 1.3 times 10 to the negative 4th.